Okay, so thank you, Bill. Good morning, everyone. So in the next 45 minutes, my task is to basically tell you what reality is with respect to scheduling a big heterogeneous GPU supercomputer using PBS Pro, by the way. And despite all the claims that GPUs are, of course, one of the best things to happen to HPC in the last several years, putting it in a workstation is one thing, but scheduling this with thousands, I mean, there are 4,000 GPUs in TSUBAME2, is something a little bit different. Of course, the capabilities are different, but also there are lots of additional research engineering that has to go into the system to make it work. So today, hopefully I can introduce you some of the things we did on top of PBS, what we achieved on top of PBS Pro, and also tell you a little bit about the future as time allows. So, just to give you a little bit of historical perspective, so Tokyo Tech is a one of the major universities in Japan. We're like, in some sense, we're like MIT, as the name implies. It's the best technical university in Japan. But also, we are one of the, we host one of the national supercomputing centers. So, just to give you a little bit of historical perspective, TSUBAME1 was launched in 2006. We're the first supercomputer in Japan to supersede the Earth simulator, which was #1 supercomputer in Japan at the time, and of course was #1 in 2002. By the way, we were not using PBS Pro at the time. We're using. I'm not going into which workload scheduler we use, but.
It's okay to say who you replaced.
Okay. Right. Okay. It was a Sun's workload manager at the time. Yes. Now, so the plan was to basically try to accelerate because the power, we were very much capped on power, and we needed to basically not increase the power to achieve better efficiency, but basically to stay within the same power envelope, about 1 megawatt, and under normal operations. And of course, at the time, the solution, the GPUs was just coming out. We were doing some basic research, trying to accelerate applications using GPUs, and we're successful. So we were, the next step was obviously large-scale deployment. So TSUBAME2 was being planned, and we put in some initial GPU. In fact, TSUBAME1 was the first machine to be retrofitted with GPU, but it was the first machine in the world to be on the top 500 using GPU way back in 2008. And at the time, we put in something like 650 GPUs in the entire machine. But this is a retrofit. And as a result, there were lots of compromises we had to make with respect to performance, especially the lack of internal bandwidth in the system. So with TSUBAME2, we started from scratch. We worked with several vendors, of course, NVIDIA, but also with system vendors like HP and NEC to design the system from ground up. Back in 2010, there weren't really any servers that was appropriate for putting in massive amounts of GPU in dense configuration. Now it's pretty normal, but it's back in, when we're designing a system back in 2008, 2009 timeframe, a lot of people were saying, well, we're going to put one GPU in a system, but we have a 4U chassis. So that wasn't going to work. So we built a very dense server, it was essentially 1U, but half U, but 2U height, but half width form factor, but 3 GPUs, very deep. And then, of course, it was also a scale-out architecture because we needed bandwidth, and unless we have bandwidth, we can't really scale out. So we worked with HP considerably to design the server, and then the result was with over 1,400 nodes, and about 4,224 GPUs to be exact, in the entire system. The first incarnation was 2.4 petaflops. Later on, we upgraded to the latest GPU, which was then became 5.7 petaflop machine in 2013. And And then we need a workload manager that will scale to be able to schedule jobs across 4,000 GPUs in the system, and the choice was to use PBS Pro. And just to give you a little overview, we have, of course, 7 petabytes of storage, lots of optics, about 100 kilometers of fiber, about 3,500 full bisection battery using DRL InfiniBand, about 3,500 endpoints, and corresponding optical fiber. That gives us about 7 gigabytes per second end-to-end on arbitrary connection, and so the total bandwidth in the system is about 220 terabits per second. Lots of cables, yes. Imagine putting it in, but imagine tearing it out. It's going to be a chore. So TSUBAME2 became number 1 in terms of the the greenest production system in the world, according to the Green 500. The absolute ranking was number 3, because the top 2 were experimental systems, but also, of course, became number 4 on the top 500. So it was pretty big, pretty large system. And with respect to greenest, we were about 3 times more power efficient than a laptop, according to the same measurement. So supercomputers are pretty power efficient, and now it's even more. Just to introduce you to a few of the applications that are running on the system. Of course, we have thousands of users on the system. In fact, everyone on campus, Tokyo Tech, gets an account. So theoretically, we have about 10,000 users. But not, of course, everybody would use it as a supercomputer. Your first-year undergraduate will only get a small resource. But we do have about 2,000 supercomputing users, because we're also a national center. So the majority of the resource is being used to serve the national needs. And of course, there are a variety of applications. There are lots of interesting applications. For example, this machine, there are a few people using the machine to solve pure math problems. I was totally blown away when a pure math professor one day came to me and said, he thanked me, said, "Why are you thanking me?" "Well, because you built, we facilitated this with a big supercomputer. But you're a pure math person. Why are you using a big supercomputer?" Well, do you know the graph coloring problem?" "Yes." "Well, that was solved using a computer at the time. Now we have much more sophisticated topology problem that we need to emulate, like 16 million proofs. And that was going to take tens of years, but with the machine, it only took 2 months. So he was very happy he was able to prove his theorem. But so that's one case. But have one evidence that the machine is easy to use, even by a pure math professor. But majority of the applications are really those that are basically of high concern to the needs of the taxpayers. Some with regards to safety and disaster environment, because of course Japan is a country that somehow we get lots of disasters. Even a week ago we had a huge flood, basically that wiped away 10 people. Of course, we all remember the big earthquake back in 2011 that killed about 20,000 people. Medical pharmaceutical, of course, this everybody concerned in the world, from poor nations in Africa. Of course, for us, because we're the longest we have a nation with the longest lifespan. But if you have people who live long, your medical bill goes up. And so we need to basically try to control those costs. And also manufacturing, because Japan is a big manufacturing. We're a very country. I'm just amazed at how many Japanese cars are roaming around in California. In fact, we may have more Japanese cars in California than in Tokyo. So, but also these supercomputers are important not only for the application they run, but being a computer scientist as an academic, as someone also who's in academia, it's already important for supercomputers to drive the technology. So, when the clusters came about, supercomputing took a little bit of a back seat. So downstairs, if you go, there are sections downstairs that basically, shows the greatest and latest supercomputer at the time, like Cray 1 is downstairs. and like CDC 6600, if you're old enough to remember those machines. So those were special, state-of-the-art, really advanced the field. So supercomputing kind of took a back seat when the clusters came about. But now, again, with Moore's law ending, it's starting to become the frontal leadership architectural platform again. So a lot of new technologies are now being aggressively tested on supercomputers before anything else. Well, maybe that may not true. Some technologies are being tested on something like this. But I think supercomputers and maybe like smartphones are probably the frontiers of IT. So it's really important to serve at least. So this is one industrial application. This is done by a guy named Shimokawa, a tall guy standing at the center. But this is basically sort of industrial simulation of simulating how when liquid metal would solidify, the microstructure forms what are called dendrites. And this the composition of the 3D structural composition of these dendrites determines the characteristics of the metal alloy itself. And you want something that's lightweight, so you want these tree-looking structures to be fairly sparse but also entangled. And but since these are very highly dense materials, and also these are very the phenomena is very nonlinear. It was very, very difficult to simulate because it was going to take petaflops of compute power. Well, so team led by Shimokawa and also by Professor Aoki, and we also helped out in tuning the code, basically achieved 2 petaflops on this code, which made this simulation, like 3D simulation like this possible. And now it's running at 3.4 petaflops on TSUBAME2, 2.5 version. And this is the first time a simulation was like this was possible in 3D. And obviously, if you run this in 2D, you can get some results, but it's very obvious it's useless. So you really need 3D and a sizable structure for a simulation to be useless, only possible with the petaflop capabilities of these machines like this. Another example is a simulation of the entire city of Tokyo with respect to wind flow. And now they're extending this to have thermal component. So to be able to simulate how, for example, the air would be trapped inside Tokyo and would elevate the temperature. And this is also serious in countries like Singapore because of the global warming effect. So basically, they have to simulate the city wind flow with turbulence at something like 1 meter resolution. So that's 10,000 by 10,000 by 500 grids. So it's massive amounts of grid, and also they have to be able to simulate turbulence. So they used advanced, highly parallel LES lattice Boltzmann code, but also incorporated a turbulent flow model. And of course, they had a entire structural map of Tokyo, essentially, the topology as well as all the buildings. And this was done by Onodera and Aoki. And so this is, again, entire Tokyo. If you've ever been to Tokyo, this may look familiar. Here, right at the center, here's the Imperial Palace. Here are the skyscrapers near Ginza and Tokyo Station and so forth. Here's University of Tokyo. So this is 10 kilometer by 10 kilometer. But again, this is a 1 meter resolution. So just, 1 meter is like, someone that's sitting next to you, it's 1 meter. So it may look smooth, but if you look at the detail, these are skyscrapers in the Shinjuku district area when they have high concentration of skyscraper. So you can see that there are lots of turbulent flow. And then this kind of technology, of course, for city planning can be used to assess the effect of what if kind of scenario. What if you build a building here? How it's going to affect the environment? If you have a thermal component, and like they're doing now, you can predict how the city might be susceptible to this heat island phenomena, that hot air is trapped. When there's an explosion of a certain nuclear reactor, 100 kilometers away north of Tokyo, and the wind is coming your way, where will the radioactive components will be deposited? there are all kinds of applications. And of course, if this is oblivious to the structure, so something like this can be used to simulate cars at millimeter resolution as well. And they have actually done that. Health applications. So this is a result achieved by people in Italy using a machine. So this is to simulate the blood flow along your arteries. But every artery is different, so the idea is to take a CT scan of your artery, and then then pump the blood. But they really want to do this in ultra high resolution, because there are about 10 billion degrees of freedom to get sufficient resolution for doctors to be able to use them. So, but they were successful, and it runs at about 0.6 petaflops, and this won the consolation prize of Gordon Bell in 2011, the same time as the other one. So we won 2 Gordon Bells, won the main prize, and this was the consolation honorable mention prize. The bad news, of course, is that even with this, running at 0.6 petaflops of 4,000 GPUs, the turnaround time is 40 hours. So they need to shrink this down to like 2 hours to be usable in medical clinics. So you need to be able to fit something like a 50 petaflop supercomputer in a hospital. But that's probably coming in the Nexus-Go era, so it's going to be interesting. Industrial apps, we also support industry. There are about 200 companies. There have been about 200 companies who have used TSUBAME to date. One company is a company called Toto. You may see some of their products in the US as well. They build sanitary equipments like the ones you see here, which is very important for your livelihood. Yes, but what they want to do is to build a very water efficient one. And this is, of course, precisely what you might need in California these days, right? Because toilet bowls actually consume lots of water, but some of the most water inefficient ones use about 10 gallons of water. And the most water efficient is like 18 liters, but apparently it's really hard to clean everything. I won't go into details of what they're cleaning, but with only 18 liters of water. So they really need to simulate this, but it's really hard because this is a multi-phase simulation. You got water, you got air, you got very complex 3D geometry, and besides, when you have a very water efficient toilet, the flow of water along the 3D geometry is really, really thin. So we really need a very highly accurate simulation, or it's not going to be useful. So although they could have the technology simulate, they were really frustrated with the fact you see on the right-hand side. They are able to simulate, but it looks fine in a Hollywood movie, but it's not as far from reality. It doesn't match the physics. Whereas they were able to parallelize the code on TSUBAME using about 200 GPUs. And if you look, the bubbles, which are very important for cleansing these the surfaces, is vastly different. And actually, one on the left-hand side matches the physics very well. So now Toto is now starting to design these sanitary equipments using supercomputers. And when I told this to a rival company in Japan, they were just blown away. Using supercomputers to design toilet bowls. So in order to penetrate the industry, you just need one uptake of a company that would be leaping far ahead, and the other companies will likely follow. Finally, medical. It's very important, and one type of disease that's really prevalent in developing countries are what are called NTDs, neglected tropical diseases. So these are types of these diseases that are neglected because it's very low profit business for pharmaceuticals, because great drugs, but you want them to be expensive, but it's very hard to sell expensive drugs to developing countries. And there are several of these, and that's actually infecting about 1 billion people, and there are about 500,000 deaths. So we're worried about death of several hundred people, but actually these diseases are killing 500,000 people per year. So it's really important, and actually our Prime Minister, Abe, basically promised that Japan will be aiding the African countries back in 2013. And what we're doing, and I'm sorry for the Japanese on the left-hand side, but that's a Nikkei newspaper, just like Wall Street Journal in Japan. And that's to say that now TSUBAME is being used to create drugs for these neglected tropical diseases. And there are about 20 million compounds they have to filter from. And our scientists, along with the Asteris pharmaceutical, is using the latest state-of-the-art methods, including not just molecular dynamics, but structural proteomic docking, even searching the literature and data mining the literature in order to narrow down the appropriate substance from 20 million to 20. And they're almost there, apparently. So despite the fact of all the promises of big supercomputers being used for pharmaceuticals, actually the real success rates have been low. But with power, with petascale computing power, now it's becoming a reality. So I told you about the upgrade, and even with the upgrade, it's been fine. If you compare the K computer, which is the fastest supercomputer in Japan, which is about 11.4 petaflops, TSUBAME 2.5 is now in single precision, and that are important for many of the applications that we've shown you today, actually. Most of those apps are running at single or in hybrid precision. We're actually faster, 17 petaflops peak. And double, of course, K is faster, and also K has more memory. For some applications, K is faster. So you can think of the two machines to be pretty much equal in terms of their capabilities. The difference, of course, is the K computer took about $1,400 million to build and maintain over 6 years, and we're using like $45 million. So it's about a factor of 30 difference. And a lot of people ask me why that's so. I mean, do I have humongous bargaining power with the companies? And well, that may be so, but it's not sufficient to overcome a factor of 30 deficiency. There's just no way I can do that. If I have such a bargaining power, I wouldn't be here. I'll be cruising to Bahamas or stuff like that, retire. So why is that? Well, so if you look at this is what I meant by saying supercomputers need to be the forefront of technology, even if they're commodity-based. The word commodity is misleading in saying, a lot of people take the word commodity as meaning saying, it's cheap. But actually, commodity is not cheap. I mean, iPhones are almost $1,000. But, they contain, the state-of-the-art, now with 6 plus. This is still a 6, but with 6S and 6S plus, they're using 16 nanometer fabrication technology. They have high-definition screen. They're using the latest battery, so forth. And so actually, commodity really is the state-of-the-art because of the volume now. It's very different in IT compared to the other industries. And the same is true for supercomputers. If you compare the technologies between TSUBAME and, say, a K computer or even BlueGene, you can see that, for example, the number of threads are greater. We're using faster memory technology, using GDDR instead of conventional DDR3. We're using silicon photonics, as you have seen, with massive amounts of silicon photonics, whereas other computers using still conventional copper. We're using SSDs on all the nodes. TSUBAME was one of the first supercomputers to use SSDs on all the nodes to accelerate I/O, called burst buffers, but they don't have such features. And we have very active power management, but they don't. And we're using also cloud technologies like virtualization technologies to better efficiently use the resources. Well, why they don't have such a support. So all of these combined gives us the most cost-effective solution while not sacrificing performance, allows us to sustain our level of confidence. But of course, no machine is good without good system software to manage it. So we have a trajectory for TSUBAME2. I'll talk about it later if I have time. But we have basically, we're right now in the process of designing and procuring TSUBAME2, which will be commissioned in 2016, and hopefully we'll have about 20 petaflops of compute power. Just to give you a little bit of what we do with the batch queue, with resource provisioning, some of the research and development we've done. So when you have a GPU-based computer with, that are fat nodes basically, containing multiple CPUs and also multiple GPUs, scheduling these is not a trivial problem, because the conventional wisdom is, you have a batch queue, you submit something, of course it's dispatched. But the user's view does not necessarily match the physical configuration of the machine. So users may say, well, I need 20 nodes and 2 GPUs and 1 CPU each. And you can see that this doesn't match the physical artifact, physical design of the nodes. So there's a mismatch here. So, so the simple way of solving this is to say, well, you got 2 GPUs, 1 CPU here, we're just going to give you the entire node. But this is hopelessly inefficient. So what do we do? So, so we have TSUBAME2 have 3 GPUs per node. In the ideal world, we have, we have OpenACC or CUDA for intra-GPU parallelism, OpenMP for intranode multi-core CPU, multi-GPU parallelism, MPI for internode parallelism. And the jobs will use all the resources in a node. But in reality, this doesn't happen. We've been running millions of jobs, but this is not the normal case. The reality is there are 3 types of workload. One is, of course, CPU only. And other is intranode and multiple GPUs that are like strong scaling or ensemble, like for example, molecular dynamics. And then there are scaling applications like the ones I demonstrated to you, like like these big CFD applications. These are MPI weak scaling, and they may use OpenACC or CUDA plus MPI, and single GPU per MPI rank. So, and when you ask a programmer on any of these 3 applications, can you use the entire CPU and GPU? And the answer is usually no. So usually, the jobs are either A, which is CPU only, or in case of B and C, it's mostly GPUs. So what do you do? And also, GPUs are split into different configurations, even, again, that doesn't reflect the reality. So in TSUBAME2, what we have done not for all the resources, but about the 40% of the resources, of the nodes, what we have done is to take a single node and virtually split it into 2. Into CPU portion, which with the majority CPUs assigned to using and encapsulated using virtual machines, and particularly we use KVM. And then we have a bare metal portion, which takes on the remaining actually 4 cores, 1 for each CPU, GPU, and 1 for network to drive the InfiniBand. And the nodes, again, are isolated using KVM. The CPU portion is isolated, so there will be people who are asking only CPU jobs don't inadvertently or maliciously utilize the GPU, and somebody schedules something and fails to avoid that situation. And then give these split nodes onto the users. And this has proven to be quite beneficial. So TSUBAME2 is currently operating in this mode. So if you look at our performance workload statistics, by the way, which is open to the public, you can see that there are more virtual nodes than physical nodes, just like clouds. So TSUBAME has 1,400 nodes, but you see something like 1,700 nodes in the system. This is fine, but when you look at the statistics of how many GPUs are being utilized, and this is TSUBAME's GPU queue, GQ, there are, again, different types of workloads use different number of GPUs. So, so the light blue portion is what we're expecting. We have 0 idle GPUs, that the jobs are using all the GPUs in the system. But you also see orange, green, of course, white. White is somehow the GPUs are idle. And the green is people are using only 2. So one GPU is just remaining idle because people sometimes want even number of GPUs per node. And orange is 1. So so in order to best utilize resources, we need to figure out how to utilize this. And it's not that the system being underutilized. You can see the blue line there is the number of waiting jobs that are waiting. So despite the fact that there are waiting jobs in the queue, there are idle GPUs, which is bad. So this is what we call idle GPU scattering problem. So GPUs are kind of scattered because of the physical artifact of these fat nodes. Don't match the job descriptions. A lot of resources remain idle. By the way, this is not just a problem with GPUs. This actually has been a problem for memory, and also even for stuff like memory in the system. Some systems underutilize their memory. But in particular to GPUs, it's because it's hard to migrate. It has been hard to migrate the jobs. This is something that happens, and also because GPU resources are expensive part of the system, you don't really want to underutilize them. So the ideal case, this is sort of like a sketch of a TSUBAME2 architecture, and we have like 7 to 8,000 chips in a system. This is a sample configuration using something like 2 Broadwells and 4 Pascal GPUs. This may not be the actual figure. We may have alternative architectures, but this is a sample. And what we want to do, given these 2 CPUs and 4 GPUs, the ability to split them up, for example, like this, like intranode, this will be 4 GPUs being served for intranode jobs, predominantly GPUs, but also the bottom part, that is there are CPU jobs running simultaneously using OpenMP, and so these will be sharing the nodes. Or we, in some cases, would be just splitting up the nodes virtually like this. So there will be 4 MPI ranks, but these will be isolated, so to protect the memory allocation, and then at the same time still facilitate the OpenMP jobs. So we want to be able to do the splitting, of the arbitrary splitting of the resources, and this is just like what cloud centers do. The only problem is we need to do this in a supercomputing setting, so no performance compromises, and also the workload manager has to be aware of this. So we are working with various batch queue vendors to say this is what we need, including Altair, of course, and hopefully something like this will be facilitated. We're also going further in our research. How do we solve this problem even better? So, because when we have idle GPU in the system, there are certain technologies to utilize GPUs across the nodes. That is to virtualize the remote GPU. And then, so even when we get jobs where we can't meet the GPU demands, we can use the idle GPUs, but also allows the system to pretend as if it were local by using network virtualization. This turns out to be an expensive solution, as you can imagine, in terms of performance, because all the GPU memory transfer has to go with a wire. So then we devised new technology to basically be able to migrate the GPU context across the wire. Only once, by the way. We can't do arbitrary migration, but we can do one-time migration. So we can basically localize what it says remote right there back to from node 2 to node 1 when the GPUs in node 1 that have been occupied by some other job becomes idle. So this one-time migration, we developed technologies for arbitrary GPU. And then we're working to extend the scheduling algorithm to the best efficiently schedule the jobs given this assumption. So since lack of time, I will skip the technology called mRCUDA. There's already existing technology called rCUDA that's just a remote virtualization GPU that's being developed in Spain. And this is similar to rCUDA, but we also have added this migration feature that allows more efficient usage resource, because this is, for example, running lamps, one of the HPC applications, across the wire. So you can see that there are lots of, the red portion is the InfiniBand overhead. So you can see that for this particular application, InfiniBand overhead just overwhelms the overall execution time when running over the wire. However, but we still can schedule stuff ahead of time. That was the benefit. But then this benefit is canceled out by the fact that this execution is slow. So by being able to do this migration, I'll skip over the details, the system is able to allow this migration to happen when things become idle. And our simulation studies show that the overhead under this scheduling gets greatly reduced, almost to like zero, because of this ability to consolidate to be able to become a local resource. So you can see that here, the overall overhead is almost like zero. So we're greatly enhancing the application speed. And this also allows the overall job execution efficiency, the throughput to be increased. So you can see here that the top part is a conventional first come first serve type of scheduling, whereas the MRQ, which is our scheduling algorithm plus this consolidation, you can get about 10% increase in the throughput, overall throughput of the system. So if you think 10% is not, well, it's not all that great, actually under a very heavily congested system like TSUBAME, there's significant improvement in your overall job wait time. So again, the simulation studies show in these highly congested system, being able to schedule resources, because we can consolidate virtually first, allows us to head start the execution way ahead of time. And then at certain points we consolidate for better efficiency. So our waiting time decreases significantly while not losing performance. That gives us best of both worlds. So this is sort of ongoing research. Another thing we're doing, this is more of an engineering problem. So there's a we all know the concept of backfilling. So backfill, we thought would be effective, but it turns out backfill was not very effective on TSUBAME2. And we said, well, why is that? It's supposed to work. This is old technology. So it turns out that a lot of people were specifying as their job make span 24 hours, even though the job may finish in 30 minutes. And why do the users have this bad behavior, sloppy behavior? Well, that's because there's no penalty for doing any bad behavior. Users are like child. No, sorry. Have to train them to behave good. So there are several, of course, usually like people have job batch scripts and they don't want to change them. There are minute details with respect to why they can't adjust their job time. But if you have user behavior like everybody's submitting for 24 hours or more, obviously backfill doesn't work, because there's just no empty backfill slot to fill, because jobs are artificially inflated in their wall time. So what we did was to say, well, we're not going to, previously we charge your allocation just for your running time, that is your make span. I'm sorry, the make span. But we will also start charging you for your declared wall time. So, but in a minor fashion. So, of course, the users, when we told users this, they really didn't understand. So basically, we waited for 4 months, saying, here is your current charge, but this will be your new charge under the new program. Give it a grace period. So this says, well, without going into details, and if you're interested, we can give you a lot more detailed technical exposition of this. So basically, if people predict their runtime well, they get charged less. But if they grossly of course they underestimate, of course they get cut off. But if they grossly overestimate, then they get charged heavily. So there are a lot of discussion that went on into coming up with the correct formula. But this is to incentivize people for making the right declaration about their job execution time. So we've been monitoring whether this will be effective, and of course there's some artifacts of some big number of jobs, certain type of jobs being submitted. But overall, if you look at the trend of the graph as we go right, this is the share of the jobs basically that says that they predicted correctly, that they get a discount. So the number of jobs that get a discount across the queues, there's a slow trend of an increase. And we did some statistical analysis of this. And yes, in fact, the number of jobs that are predicting correctly has increased because of this incentivization. So, of course, there are some problems because charging function may be too complicated. Well, it's only a linear function, so Tokyo Tech and also all the users across the nation, mostly scientists, so they should be able to understand linear functions, but still, some people say it's complicated. Some applications are naturally, it's a bit more difficult to estimate their runtime, like search algorithms. Right now we advise users to checkpoint those, of course. One idea we have is like clouds have some ability to have elastic allocation to expand their execution time. Of course at higher charge, but some elasticity in this respect will likely help, and we're saying, again, telling our workforce resource vendors to whether that kind of feature would be amenable. And of course, the future research is to do better prediction of the runtime, so we can do some of these things automatically. And there are several papers. We have tried this in TSUBAME1, some of the earliest statistical analysis done by people at Santa Barbara, and there are some good papers that have come out because of the machine learning craze, and there are very good predictors now, so we might actually be trying those as well. Finally, the power. So when the great earthquake hit, that basically blew away one of our nuclear reactors, Japan had to stop all the nuclear reactors, which is bad news because at the time, 20% of Japan's electricity was being generated by nuclear reactors. So when you take away 20%, and this was March, but summer was approaching, and summer, is where when everybody turns on air conditioning, and there's like a factor of 2 increase in electricity consumption during summer daytime. But we didn't have capacity as a nation, so everybody was asked to basically save power during summer daytime. But our machines don't have the capability to do power capping. So we went and implemented this. So we basically said, well, we will be power capping during daytime. During summer daytime, between like July through early September. During the daytime, we can set a power cap goal, we'll say like 800 kilowatts. And then, during nighttime, we can release the power. We can release the caps so people can run at will. So we have implemented this on top of PBS Pro, and it was a fairly easy implementation. Right now, there are various ways to cap power. Right now, we take a simple approach of actually turning the nodes off dynamically once they come back finish their execution. And then, the workload schedule, the PBS Pro will hang on to the node and not schedule them and just turn them off. And there are lots of intricacies actually involved. Like, when you reboot the node, it may not actually work, but so we have to go through all these contingency to make sure they reboot again. So these are cloud-like features. But largely, this is implemented and it's working. So you can see now, if you look at also we make our power monitor public. So if you go to our website, look at our power profile, you can see that during the day, during weekdays, during summer days, even right now, the power is capped at 800 kilowatts. It doesn't go above. And of course, we want more sophisticated power control. So again, this is something that we mandate. So I'm running out of time. So just tell you what TSUBAME3 I've finished. There are several big goals. One is towards exascale, and one is big data conversions. But just to tell you what TSUBAME3 will look like, it'll be like a 20 petaflop machine. It'll have massive bandwidth and with lots of silicon, both in photonics and storage, and non-volatile memory, and we'll have advanced power management and so forth. And we're doing advanced tests because some of the goals we established at like 10 gigaflops per watt for TSUBAME3 generation is actually very aggressive. But this is something that we have to meet in our overall technological goal to exascale. So 10 gigaflops per watt for TSUBAME3, we may be able to meet it, but of course it's very tight. So we're doing several tests. For example, we have built the TSUBAME KFC, which is a prototype. It's using various advanced technologies like immersive cooling being provided by Green Revolution Technologies. And it's in a container. It's using ambient cooling, so it has no chillers. So the oil loop, this is an oil tub. And this is soaked within the oil tub. Is extremely high density GPU configuration machine. So the oil will be about 40 degrees Celsius, and the water loop is at 25, 35 degrees, which is much higher than TSUBAME2's cold water loop. And this is all in a container, a very dense configuration, and so forth. So even with this, we can fit about 210 teraflops in double precision and 630 teraflops in a single container. If you use the latest technologies like use K80 or you even use I'm not supposed to disclose the Pascal performance, but if you use a K80 class performance, this performance is more than double. So we can fit over a petaflop in a single container in this configuration. And we won the Green 500 back in 2013, 2014. And this, of course, the goal is to basically use this kind of technology to improve on the green efficiency. But this is not only a result of having a hardware which is power efficient and cooling infrastructure that's power efficient, but ability to be able to control power, to manage power in our applications, and to get the best power efficiency out of applications, not just with the hardware. Okay, so I think my time is up. There's all this big data stuff I could have talked about, but I'm sorry I have to skip over all these. And just to tell you, just one lesson is, so maybe I'll have another chance to talk about this, but it's really, one final word is, it's really important for the HPC and big data to converge. And it's important for two reasons. One is, of course, obvious. Some of the big data workloads, like being able to handle extremely large graphs. Just show this slide. Being able to handle extremely large graphs, being able to do extremely fast analytics, something like deep learning. These are extremely compute or bandwidth hungry applications. So in the past, when big data started emerging, it was largely, there weren't very heavy workloads. But now the capacity of data being handled by these big data workloads are so massive. But also the analytics being used either in discrete algorithms like graph word sorting, or things like deep learning, which is essentially multiply add. That's linear algebra, have exploded. So in order to accelerate big data, the best platform is an HPC platform. So now big companies understand this, like Google and so forth. Not all data centers understand this, unfortunately. But it's really important for HPC and big data to converge because of the needs of workflow. For example, the Graph 500, which is a benchmark for large-scale graph analytics. So we are right now running on some K computer, unfortunately not on TSUBAME. We run on TSUBAME, but K is the fastest platform we can find running this. And so the K is the fastest graph processing machine in the world, using the algorithm being developed by one of our students and other colleagues. But even so, this graph algorithm, 70% of the overall compute time is consumed by network communication. So it's a highly network-bound, so extremely highly tuned graph algorithms are highly network-bound. But most interconnects in the cloud are gigabits or at best 10 gigabits. And there's just no way they can run a very fast graph algorithm because Ks and TSUBAMEs have 10 to 100 times faster network compared to these cloud infrastructures on something that you acquire just out of Amazon. So you really need supercomputing infrastructure in order to accelerate these. The other need is that there's imminent end of Moore's law. And when Moore's law ends, we'll not be able to increase our compute capacity anymore because Moore's law will end. So, and this will come in about 10, 15 years. So if Moore's law ends, companies like IBM, so forth, may be in trouble because if Moore's law ends, your computers, your flops will not increase. So there will be no incentive to buy a new machine if you're relying on flops to increase your performance. So it'll be like your old car. Or so computers will become like refrigerators. Do you replace a refrigerator every 3, 4 years? No. You may replace it every 10 years or 15 years when they break down. But can IT vendors just do business in that kind of business cycle? Probably not. So we need better ways to accelerate our top high-end applications, but without using flops, but using bytes, bandwidth and capacity. And we're in the process of working with various people to design a better architecture for the upcoming imminent ends of Moore's law using heavy use of next generation storage, next generation packaging technology, next generation optics, blah, blah, blah. So it's really important. So, but these are fundamentally can be classified as data technologies rather than compute. So it's really important that when we can fit a K computer, for example, in a single tub, and we have design studies that allow us to do that, that we can actually, but we'll instead of just using flops, we estimate that we can fit 10 petaflops in a single box. But what's better is we can fit a much higher capacity memory and storage into the same box compared to, let's say, the K computer today, which has 700,000 DRAM DIMMs, by the way. So it's not a shabby machine. Well, almost a million DIMMs. So, but we really need big data technologies to accelerate HPC of the future. So with that, I'm sorry I had to skip over materials, and we're doing studies in that direction. But hopefully you got the message, and I'm happy to take questions if you have time. Thank you.
Thank you. Thank you very much. Time for a couple of questions.
Least technical guy in the room probably asking a question. Sam recently sent an article to me. Sam, talking about you, sent an article to me. I don't recall the author or where it came from, but talking about MPI and sort of the death of MPI and within that article, the death of HPC. I don't know if you saw that article, but I'm curious for your view on MPI and its future and some of the new technologies that are coming around to replace it.
Yeah, so the question is basically, what are the emerging alternative programming model other than MPI for doing massively highly parallel programming? Well, of course, there have been, in fact, for many years. If we go back to the days of like high performance Fortran, there have been many types of work that try to deal with consolidating these distributed systems with their distributed memory, giving them single address space image in order to make programming easier. And this has been largely inherited with things like PGAS languages like Core, Fortran, and so forth, UPC and so forth, and now Cray had Chapel. The acceptance of these languages have been fairly slow, partly because of performance issues, and HPC is about performance. So people don't really accept something that will go slow, despite the efforts. However, there are lots of evidence that this actually may be the way of the future. One thing is now we can have very good MPI interfaces, especially like MPI 3 and beyond, that allows for standard implementations of these languages using very highly efficient hardware features afforded by things like the latest generation InfiniBand or OmniPath. So like microsecond, for example, being able to access remote memory with 1 microsecond latency, remote put and get, but very extremely fast. So I think it's not death of MPI, but MPI underneath, because it's standard, will allow these high-level languages to be sitting on top of the MPI and to facilitate them. So in a nutshell, because MPI has evolved and have become fast and ubiquitous, these PGAS languages, for example, can now become truly portable and not just code portable, but performance portable, such that it may be able to spread. And this may also go for things that are more converging with the big data type of applications. So I think it's more of a it's like saying, is assembly language dead? Well, assembly language will never die because it's inherent. But people will move away from assembly language programming, and MPI is like that.
Am I still on? Okay. Anyone else?
There's a question over there.
I can always count on the question coming from whichever direction I'm walking away from.
Just a quick question on when you started using KVM to split your nodes up, did you see any performance problem both from a CPU perspective and also from an InfiniBand perspective?
Yeah, so the question is when we did a virtualization, what were the performance issues? So because we did this very early on in 2010 when technology like SROV didn't exist and we're still not utilizing those, what we did was to make a decision to, on the performance side, that is GPUs and InfiniBands, this will be still done bare metal, whereas the virtualized part, we will be sacrificing performance, because then it will have any sort of external communication will have to go through the virtualization layer. But of course we told users that, and then said, well, if you are willing to run, if you have an intranode parallel, just a straightforward OpenMP program or something like that, or pthread program, using 8 to 16 cores, well, this will be a perfect resource for you, and we'll give you a discount. But if you want large-scale resources, you can run MPI, but don't expect it to be fast. So this has gone very well. Having said that, and of course we did, the obvious, we basically tied all the CPU cores to the VM, and did all these tuning to alleviate the problems associated with this co-location. Having said that, now it's 2015. There are all these technologies out there, including containers, including SROV, and other artifacts that allow you to do these kind. Also, various types of dynamic deployment, or like OpenStack and so forth. So we're looking at designing a holistic system that allows you to be much more extensive, to be more container-based and having but very little performance overhead, despite these virtualization, or at least containerization. So that'll be our next generation machine. Jury's out as to whether we will see significant performance overhead, but we expect, so far the studies show there's very little, so we'll see.